Okay, let's start off with a quick discussion on the nature of sound and MIDI. So what is sound? Well, in short, it's vibration. Here we've got a photo that shows a speaker propagating a waveform, sending it out. It causes molecules in the air to vibrate, and those molecules in turn cause others to vibrate, and so on until eventually it hits the ear. Below that, we can see a waveform that shows how it moves up in amplitude and down in amplitude, which creates compression and rarefaction. We'll talk about that very soon. So what's happening is that vibrations are moving through a medium that contracts and expands to propagate a repeating cycle of moving molecules that eventually strikes the ear, and then through the magic of biology is converted into electrical signals processed by your brain. This works unless you are in the total vacuum of outer space. So as long as you're in some sort of medium, it will carry vibrations. For example, you have air, which is a mixture of oxygen, nitrogen, CO2, and other gases. This will affect how you hear things. You'll hear things more or less as normal, although the composition of gases can change, and that will make sounds sound different. If, for example, you have more helium, you will have a higher pitch. The vibrations will occur at a faster rate. If you have more nitrogen, you will hear a lower pitch because the vibrations are occurring at a slower rate. Similar, water. You can hear sound underwater. If anyone's ever gone in the bottom of a pool and tried to listen to people talking, or a bathtub, you can definitely hear the sound through water or other liquid media. Same with solid objects. Because they're not really 100% solid, there's still space between molecules where they can be pushed together and compressed, and then they snap back to their position, demonstrating molecular elasticity. All of these will help create sound waves when the molecules are pushed together and then pulled apart in a repeating sequence of events. The energy of the sound is transferred from molecule to molecule and space to space, repeating this process of compression and expansion until the energy of the wave gradually dissipates due to distance. There is a finite distance that a sound can travel. There is no infinite sound. It will eventually lose energy as it's traveling over distance. So a couple of technical terms. When the molecules are pushed together and smushed into a smaller location, it's called compression. When they then spring back to their original location and clear out that compressed space, it's called rarefaction. The process of transferring the energy of the sound from molecule to molecule via this compression and rarefaction is called propagation. This is how the waveform is generated. It's propagated by compression and rarefaction. There are two types of propagation. If the wave moves in the same direction as propagation, so if it's propagating on a horizontal way and the wave moves horizontal, it's a compression wave. If, however, it moves in a different direction to its propagation method, then it's transverse. That would be if, for example, the source is moving up and down on the vertical, but the wave is still moving horizontally. So here we have a diagram of a waveform. You have a center line that shows relative null pressure, and as the wave moves upwards on the vertical axis, you have compression until it reaches a peak amplitude. Then the compression moves out. You have that elasticity of molecules going back to their initial state. Then it hits the 0 point on the center line again and keeps going until you have total rarefaction. This is when it's back to the original state and nothing is being heard. Basically, you will have essentially the inverse of the compression at that point. So if the compression is 1, the rarefaction is going to be -1. The wavelength is the measurement from any point of either the compression or rarefaction aspect of the waveform to the next point. So compression to compression, from an entire cycle of the wave going all the way up, all the way down, and then back to the zero line, or from the very top amplitude to the next peak amplitude, or from the very bottom amplitude to the next bottom amplitude. That will give you one cycle or one wavelength. Up here in picture A, you have the compression wave, and then in B, you have the transverse wave. In A, the spring is being pushed and pulled entirely on the horizontal, and that gives you a compression wave because it's moving still only on the horizontal axis. In B, the hand is moving up and down, and the wave is primarily propagating on the horizontal axis left to right. So that would be a transverse wave. So that's a little bit about vibrations and how they create sounds. We'll get into more of that pretty soon. But what is MIDI? MIDI is something you've probably heard of a lot, but the long and short of it is it's instructions and not sound. In fact, it's an acronym for Musical Instrument Digital Interface, and it was created in the early 80s as a way to standardize communications between synthesizers. First presented at AES in 1981, and the 1.0 spec came out in 83 with a phenomenal demo at NAMM showing a sequential circuits Prophet connected to a Roland Jupiter 6, but it really took off because it was included in the super popular Yamaha DX7 synthesizer. So keep in mind, MIDI is a communications protocol. It does not produce any sound on its own. It's just a set of instructions that tell you what channel you're playing on, what note is being played at what velocity, which creates a note on and velocity pair, when that note stops, which is a note off and velocity pair, dynamics, program changes, and information for things like sustain pedals, filter cutoff and resolution, or controls like pitch bend and modulation. Now, MIDI can be edited as a score in a notation editor. It can also be edited as a graphical sequence in a DAW. It's usually in what's called the piano roll, where you have the keys stacked vertically on the left, and then you have a grid spanning out to the right. You can also edit it in drum grids, or more rarely nowadays, there's an event list. You can still find that in some DAWs, but it's mostly used in programming languages like Max MSP or Super Collider. When you're dealing with MIDI, rhythm is measured in bars, beats, and ticks. Within a DAW, MIDI is commonly stored in a region or a clip in a track, depending on the DAW terminology. These can be moved, copied, and pasted in MIDI tracks freely. With every MIDI device, you have 16 channels of data built in, and channel 10 is reserved for drums. Here's a quick example of a graphic display of MIDI data that shows tempo mapping, piano notes, dynamic changes, velocity, and playing techniques from Dorico version 3.5. So you have the piano roll, you have a tempo map, you have dynamics, you have velocity, and you've got playing technique. It's a very nice display. And then here is the exact same data in the exact same program displayed as a score. Very cool. So entering MIDI, how do you do it? There's a couple of ways. You can do real-time entry, which is where you're playing it in on a keyboard or pad controller, generally recording and hoping that you are really close to the beat. You have step entry, which is most common for notation editors, where you're entering pitch and duration values out of time using a MIDI keyboard to enter the pitch and a computer keyboard to enter the durational value. Or, in just about every DAW, there is a pencil tool that allows you to click everything in with the mouse. One very cool thing in MIDI is the overdub or merge feature that I personally make use of all the time. This will allow you to add new MIDI data on top of an existing set of MIDI data. This is really useful when you combine it with loops and punch in and punch out. So you can build up really complex drum parts or chords or counterpoint that you just can't play otherwise. And given that I'm a pretty terrible pianist, I use this feature all the time. Another thing with MIDI to keep in mind is the ability to quantize. This is a common feature in DAWs that allows you to snap MIDI data to the rhythmic grid and fix performance errors. It's really necessary to make things align, but it does make things sound more robotic and dead. Fortunately, though, most DAWs now include a humanizing or groove factor as well that can be applied during the quantization stage.